Okay, so let me start by thanking the organizers, especially Luca, for the invitation. So I'm supposed to do what in my school I was taught not to do, namely that, I remember that in my school, just outside the library, it was written, are you here with the solution or are you yourself the problem? So here I'm supposed to be the problem. That is, I should be telling you about some open problems. Okay, so I'm a statistical physicist, theoretical statistical physicist. I work in this research institute in Bombay, TIFR, and I'll tell you about some work that I recently did with a former PhD student, Mrinal Sarkar, who is now a postdoc in Heidelberg. So what I'll do is that I'll try to motivate it and see, where does it lead to, how it can, or I can connect it to problems that generally interest the audience of this workshop. Okay. So being a physicist, I'll try to motivate it from the physics background, and then we'll see how I can motivate it or connect it to other contexts, biology, ecology, cell biology, etc., etc. So think of a porous rock. I guess we all have seen what a porous rock is. A porous rock is, it is constituted by these channels that are not all interconnected. And it is porous in the sense that it has this ability to absorb water, but then it retains it. It doesn't, let water pass through it, simply because not all channels are connected to one another. Okay, so therefore you absorb something, but you retain it. Okay, and a way to model such a thing in physics is to consider what is known as a percolation cluster. So what is a percolation? So it is the following, that you take a lattice. Okay, here I've taken a maybe a triangular, a tilted square lattice. But you can do it, you can play this game on any lattice. So you take a lattice, and what you do is that there are these bonds. So you keep some of these bonds and kick off the rest. Okay. So with a certain probability, so you visit each and every bond and you toss a coin and you say that, am I going to retain it or am I going to kick it off? Okay. So therefore, there is a number P. This is the probability with which you retain a bond, and 1 minus P is the probability with which you kick it out. For example, this is one realization of such a game. Okay. So what I do is that I start with a lattice and, I go bond by bond, and I kick it out or keep it there with some probability P and 1 minus P respectively. Okay. And so this is a particular caricature of such a thing. And as you can see, this leads to channels, not all of which are interconnected. Okay, for example, there are channels. For example, this guy, if you start from here, if you start from here and follow this path, you go this way, and then it leads to nowhere.
You start with a
complete square lattice.
Just lines without any branches.
Which? Yeah, no. So this is when you kick this out, or with a small probability. That is, there is a number P with which you retain some of the bonds, and this is above the critical threshold. So this system shows a phase transition from a point in which you don't have a path that takes you from top to bottom, to a point, to a phase in which you have an interconnected path going from one end to the other, provided you retain bonds with a high probability. Okay, so that's why I said above a critical threshold. Okay, so you get such a thing, and the game that I'm going to play is the following. Yeah. So first, let me tell you what such a structure looks like, or what are the salient features of such a structure. As you can see, this is one realization of such a lattice. So you have the following sorts of bonds or paths. For example, there's one bond, at least one bond, that takes you from top to bottom. Okay, so this is marked in red. This is CD. But then there are branches coming out of this main backbone or whatever. For example, let's say PQ, this is a branch. Okay, this is branch in the sense that it doesn't take you to the bottom, it takes you to nowhere. Okay, this is kind of dead end. Okay, and then there are these backbends. Okay, why do I call it a backbend? Because imagine, you see, let me go back to the previous slide. You see, the thing is the following, that you have water, let's say, you pour water from top, and let's say there is a gravity. Okay, this is what I've shown here. And you want to see how much of the water that you have poured from above goes to the end of the, or like comes out of this end of the rock. So there's a field which is like the gravity. And that's why I call it a backbone, because what will happen is that suppose you are here, suppose there is a drop of water which is here, it comes down and down and down, and now suppose it has to go this way, HK, it has to take this path HK, it is going to be very difficult for water to do that. Why? Because the field is pointing, pushing it downwards, but then it has to do it because if the water drop is here, and if it doesn't manage to go up this barrier, then it doesn't know what to do. It just gets stuck there. That's what makes it a porous rock. I mean, a model for a porous rock. That there are channels that take you from top to bottom. There are channels that don't take you from top to bottom. And now, given such a structure, now this structure is given to me. This rock is given to me. And on this rock, now what I'm going to do is, so first of all, if I want to study such a problem, as I have mentioned, the three salient features are there's a path that takes you from top to bottom, then there are branches and there are backbones. Okay, so an abstraction of such a thing would be to consider a lattice of this sort. Okay, so there is a backbone. Okay, just as here, CD, this is the backbone, so the backbone is here, and then there are these branches. Okay, but then you see here, different branches have got different lengths. Not all branches are of same length. So therefore, what I'm going to do is that I'm going to make this branch lengths a random variable. Okay, so I have different branches of different lengths. So there are branches and there are different lengths, and they are of different lengths, and then there is a gravity that's pushing you down. Now, if I, the way I've constructed the lattice, the structure, it is evident that the gravity is going to do both the, going to play both the roles, namely that it is going to push particles along this direction because the gravity is downwards, but then it will also push particles along this direction, so water droplets along this directions, and by doing so, it would create the effect produced by a backbend here, because suppose there's a water droplet that comes and goes down and it comes here, and now if it has to, come back to the backbone, it has to move again. So this is the structure, this is the basic structure that is given to me. This is the underlying space. And now on this underlying space, I have a walker. I want to see how do transport properties get affected by this space heterogeneity. Okay, the space is given to me. The space is very heterogeneous. There are some paths that lead you from one point to another. There are some paths that don't take you from one point to another. And then there are walkers moving on this heterogeneous space. Now, before I come to the details of this model, I mean, I was thinking, I mean, if you allow me to like think aloud, I mean, maybe you can think of it this way, let's say like, in the context of, let's say like animal foraging, it could be like this, that let's say, there is a source of water or food or something that the animals know to be existing in the southern direction, let's say north, south, east, west. So in the southern direction, they know that they don't know where exactly is the location, but they know that there is a source of water or something down here. And then there are these different paths. Let's say there's a maze, or let's say there's a forest area in which the animals are residing, and they know that more or less in this direction, there's a source of water. But they don't know exactly in which direction they have to go. And then there are these different paths, spanning out. And some of them would lead you to the, source of water or food or whatever. But there are some paths, still there is a push in the southern direction. But then there are some paths that don't lead them to any place, like anywhere. Okay, for example, this is, let's say, south, and the animals, they will be moving preferentially in the southern direction, which is implemented here through the application of this field. But then they don't know which path to to lead them exactly to that source. And there will be some paths that could lead you to nowhere, and then there would be some paths that could lead them to, let's say, the source. No, so that, okay, so the directed percolation is providing the template on which a motion is taking place. Okay, so I'm not studying directed percolation. Directed percolation is providing the structure, okay, on which there is a further motion which is taking place. I'm not asking about the directed percolation problem per se. I'm saying that the percolation has given me or has produced for me an inhomogeneous space on which a motion is taking place in presence of a bias. Okay. So the percolation, what that has done is to generate for me this random lattice structure, okay, which is to say that, you know, it has told me that there's some space in homogeneity. There are paths that, you know, take me to some point, and then there are paths that don't take me to any particular point on which I'm going. Yes, it is frozen. The structure, this lattice structure, this is what I was going to mention in a minute. This structure is frozen on which I am walking, or let's say like this, you know, these animals which are looking for food or something, they're looking for that source. Okay. Okay. So this is the model that I'm going to look at. So as I mentioned, there is a backbone and then there are these branches. Okay. And these branches are of random lengths, but this is a quenched disorder in the sense that the randomness is given for me, given to me at t equal to 0, and that's it. It's frozen in time. The randomness, this randomness, namely the branch length distribution doesn't change. The branch lengths themselves don't change as a function of time. Given this lattice structure, what I have is I have a random walker or several non-interacting random walkers, let's say. And what the random walkers they are doing is that they're performing biased random walk. Why there is a bias? Because I want to model the situation that there is something down there where, let's say, if you know, if a random walker starts from here, he would like to get to this region, let's say this region, let's say. Okay. So there is a bias, and how do I implement it in the model? What I say is that, let's say, if a random walker happens to be on this side, then with some probability or some hop rate alpha, it tries to move in the forward direction, and it tries to move backward with a different rate beta. Okay, and they have been you know, one may choose to choose you know, these rates in the following manner, that, you know, this G is the bias that lies between 0 and 1, and as you can see, alpha is larger than beta, which is to model the situation that there is a drift in the downward direction, and so therefore the particles would preferentially move in the downward direction than in the backward direction, like forward and backward direction. Okay.
I mean, these random talks, you don't put the hierarchical structure that you
No. So this is, I mean, if one would like to play this game on this structure, then, you know, it is going. I mean, this is the first step. Let's say it has all the important features. Yeah. So there is one level. So that's why I took this above the critical threshold, so that you know that there is one branch that takes you from top to bottom, and then there are these different branches, different branch lengths, and then there are these backbends and so on. Okay, so in this problem, so one finds an interplay of quenched and annealed disorder. So let me just mention this quickly. Quenched disorder is the, you know, this lattice structure, this backbone structure, backbone branches, etc. That's given to me. That's frozen in time, so that's quenched. And like, you know, what is that other source of disorder, which is this annealed disorder, because the random walker, which is moving on this structure, will once in a while go to the left, or once in a while go to the right, and so on. So it is kind of uncertain. It should not always be moving in the forward direction. Sometimes it moves in the backward direction. So that also brings about a disorder. And so the random walker is going to feel the effect of both the sources of disorder, that, you know, he is undecided. So sometimes he's moving in the forward and sometimes in the backward direction. But then when he tries to move in the forward or in the backward direction, sometimes he encounters a point of this sort when he knows that, you know, he has to go back. Okay, because there's no, you know, this point is kind of dangling in the air, it doesn't know where to go. Okay. So I hope the W is just a rate. I mean, so if you put, you know, if you put G equal to, let's say, 0, then this will be an unbiased random walker with the rate W. Okay, so this, okay, so this just scales the, I mean, this sets a time scale of diffusive dynamics. Sorry? W related to the, no, the way I've done is that no, W is not related to the, I mean, it has nothing to do, the jump is happening only to the nearest. Okay? It cannot, you can make long range jumps, but that's what I'll come to later. Okay, so this problem, it turns out, I mean, just this, I mean, simple that it may appear, I mean, it doesn't appear simple, I guess, because there are two sources of disorder. This problem has been looked, extensively in the past, starting from, several from 1983 till 2020. And this problem, this problem, by the way, is known as random comb, random walkers moving on a random comb. And this problem has been studied extensively, various features like discrete space, continuous time, discrete space, discrete time, blah, blah, blah. And, people have looked at several ramifications of this model. For example, if you have a potential pushing them towards the backbone, or you have a potential repelling them from the backbone, and so on and so forth. So I've just listed some names. Unfortunately, Ralph is not here. No, he left yesterday, I guess, but he would have been, okay. He has also worked on this model. So since I'm supposed to tell you about open problems, I just tell you, what are the main results that comes about from such a study. So what happens is that in this system, what you see is what is known as field-induced frapping. So what is it? So let me define this quantity. This is the drift velocity. So let me just go back one slide. So what I'm interested in is that there is a random walker, or let's say several non-interacting random walkers. I just let them move on the lattice, and I play the game for long enough that the system settles into a stationary state. Okay. And then what I ask is that what is the drift velocity, or let's say the average drift velocity along the backbone? Okay. Velocity meaning in the normal sense, velocity, like the distance by time. Okay. So what I want is, or let's say the current, okay, velocity or current along the backbone, because this is going to tell me if the velocity of the current is 0, then I know for sure that I won't be able to get to this point from there. And if the velocity is non-zero, then I know that some of the walkers, or some realizations of a given walker, would make it to the other end. So therefore, there is still some hope that you can get to the destination, or let's say the food source, and so on. So what I'm plotting here in the diagram here is the drift velocity along the backbone in the stationary state as a function of what? G. So what is G? G is the field that is going to push you in one direction. And what happens is that, as you may imagine, that as G increases, the velocity should increase. Of course, I mean, if there is larger push in the downward direction, so then the velocity should increase. But then what happens is that there is a critical, the velocity, first of all, is a non-monotonic function of the bias. And what happens is that it starts to increase, but then at some point it starts to decrease. And then there is a critical point above which the velocity becomes just 0. Although, the field keeps on increasing, but the velocity remains. As I mentioned here, drift velocity is a non-monotonic function of bias, and the velocity becomes 0 beyond the critical bias. And this is known as what is known as bias field-induced frapping. And basically what happens is that, this is your starting point and this is your destination. Okay. But then you see in our lattice, there are these branches. If I may go back, there are these branches of random lengths. So they come in all varieties, 2 lattice sites, 15 lattice sites, 500 lattice sites. And what happens is that if it so happens, and it is not always guaranteed, but when it happens, it does happen that there are these random walkers that get trapped at the end of a very long branch. Okay. And so if it so happens that they get trapped at the end of very long branch, and if the field is very high, the field is trying to push them. So these guys, they don't make it to the backbone. Why? Because the field is trying to push them in the backward direction. So they find it less and less likely to go back to the backbone. And this gives rise to this critical point above which the velocity just becomes 0. Yeah.
You also have some parameter that defines the speed of the source.
Yes, of course. So that is given by, that I did not mention, so that is given by the distribution of this branch length. Yes, of course. So that is what I'm going to come to in a minute, that this is a result for one particular distribution of branch length. Okay. And so what we, given this structure, you would like to know the following question, that when do we get trapping? I mean, what are the conditions for getting this phenomenon of trapping, and how do we get trapping? Okay, and no, it depends on the parameters. I'll tell you what the parameters are. Of course, it will. There is a critical point that depends again on the branch length distribution. I'll just mention when do we get such a thing and so on. So what we could do is that in this work we obtained, this is quite a non-trivial problem because there are two sources of disorder. Anneal disorder is a mild one that we know how to deal with, but quenched disorder is something which is not easy to deal with because the disorder is given to you, and I don't want to average over disorder realizations because that's not the game that I've been allowed to play. I tell you that the space heterogeneity is given to me. Given this structure, you tell me the velocity. And what we did was we could find this exact steady state properties of this model by solving this, master equation and so on. For any disorder realization, you give me the disorder realization, I will be able to tell you the velocity as a function of the bias. And the result holds for infinite as well as finite systems. You don't have to necessarily invoke thermodynamic limit, that there is a very large lattice and then you have some self-averaging and so on kicking in. You don't need that. And we have been able to derive some analytical criterion for trapping. And basically what the main result that comes out of it is the following, that if you choose this branch length distribution from an exponential distribution, okay, exponential distribution with a maximum allowed branch length, of course, you don't want the maximum allowed value of the branch length to be infinite because then you would obviously get trapping. Okay, so you would set some some number. Let's say my maximum branch is, let's say, 50 sites. Okay, and then I take these branch lengths as random variables taken from an exponential distribution.
Infinite refers this length finite, or we say false number.
No, this number of lattice sites here being okay. So yeah, so if you take it from an exponential distribution, so then this is the picture that appears. Okay, because when you have an exponential distribution of the branch lengths, then there are two length scales that come into play. One length scale is set by the exponential distribution. What is the typical length of a branch? That's one. And the second length scale is set up by the inherent dynamics of the random walker, because the random walker, they have to somehow at times go like against the field. Okay, so that brings in a length scale. How much can it travel against the field and how much can it travel in the direction of the field? So the ratio of the two is one length scale, and the second length scale is set by the exponential distribution. And so therefore, in such a case, you have such a non-monotonic behavior depending on which of the two length scales wins. Okay, so there are two length scales. One is the exponential one and one is this one. So in this case, what happens is that you have such large long branches that the random walkers are simply unable to move a finite distance against the field. And so therefore you have trapping. But suppose you take these branch lengths to be random variables from a power law distribution. That's the other representative distribution that you may think of. And the thing about power law is that there is no scale associated with it. So if you choose a power law distribution, then you always have trapping. Okay, so that's the result, and one can show it exactly. In fact, we have a criterion. I mean, these are the two distributions for which we derive the results, but the criterion is very general. You give me your choice of distribution and I can put those details into the that criterion and tell you whether the system is going to show trapping or not for a given disorder realization. I am not doing any averaging. If you want, I can do averaging, but at the moment I'm not doing any averaging. Yeah.
So the constraint is the maximum length of the
being finite.
So if you do enough realization, you will always get some non-zero velocity, right? Even if it is exponentially small, it will never be zero, right? Because even if the length of this how do you call it,
branch
is long, you still have a finite probability of exiting and going back. Always a finite.
No, it is okay. So when I say
take a lot of simulations, you will get some exponentially small velocity.
Yeah, of course, there will be some realizations for which it will be possible. For some realizations, it won't be possible. Okay, and what I'm saying is a typical realization. Of course, you have to take the limit. I mean, when I say finite, I mean finite with respect to the branch length. I mean, it is long enough. I mean, it cannot be just one or two sides. Okay, it has to be long enough. So what the way you do is that you first take the limit of this backbone sides going to infinity, let's say, and then the branch length going to have a very large value. And of course, there will be some realizations where you happen to, come to the backbone and there won't be any. But there will be happily a good number of realizations for which this thing will happen, namely.
But have you looked at the mean first or first?
Okay, so that's the thing that I want to come to, open questions. So okay, let me come back to this one. So the question is the first passage time, namely that how long does it take to get from this to that for the first time? I did not look at it. In fact, that's an open question. That it's going to be very interesting to get this number, because there will be some paths for which it is going to be a very long time to get to the end, because they may get trapped here and they have to wait till the dynamics allows them to come back to the backbone. So that's indeed. So this is one open problem. And the second one could be, I talked about just one random walker or several non-interacting random walkers, but it would be interesting to see, let's say there's a target here and there are n random walkers all trying to look for this target, and it depends on which one gets to it for the first time, and that's it, then the game is over. I can make it n interacting or non-interacting. Okay, let me come to this. This one is okay. This one is like another source of disorder that one can bring in, namely that in this game, what happens? The model that I talked about, the particle is hopping with a rate that's the same for every side. Of course, I mean there are these branch lengths being different lengths and so on, but still the particle is hopping with a rate that's independent of side. Okay, so one can try to make these rates side dependent, that okay, the space is heterogeneous, but also since the space is heterogeneous and when an animal is looking for food, I mean, he is not going all the while with the same velocity. I mean, sometimes it speeds up, sometimes it slows down, depending on where it is. And if he finds an obstacle in front, he tries to, or let's say some encounter from another species, he tries to go around that point with a faster velocity than at other points and so on. There's one more problem, I think, which is very interesting, and I don't know, like I had some discussion with Luca, which is the following, that here what I talked about is you have a point which is trying to move from, you have a random walker which is trying to move from one end to the other. But what happens if you have an extended object, let's say? Okay, so let's say, for example, there's an interface which is trying to make its path, make its way through a disordered medium. Okay, so these are what are known as spinning centers. Okay, so one example could be that, for example, let's say if you have a piece of paper and then let's say you dip it in ink or something, and then what happens is that this, the fluid, the ink that you dip it in, that gets absorbed. I mean, the paper absorbs that ink, but then you have an interface of this ink formed on the piece of paper, and that interface tries to spread or move through the paper, but the paper has got impurities, and these are distributed randomly in space. And not every, as it is shown here, not every impurity has the same ability to impede the motion. Some are stronger than others, and you have an extended object, let's say this interface, and you are trying to this is going to make its way through this like pinning centers. And it turns out that this problem, at least in the continuum limit, it has been looked at numerically, and also scaling arguments, etc., that shows that it shows a phase transition between a pinned phase and an unpinned phase and so on. So so this problem, I feel, I mean, can this be studied in such a framework, namely that there is a just as here there is a spatial heterogeneity, and that is going to, for example, if I ask how does the velocity of this interface behave as a function of this forcing field, so that is another thing that is worth looking at. And maybe I think we can discuss now. So that is all that I had for, we can talk about more. Yeah.
You have two possibilities of going down. What's the probability of each branch? Half.
Yeah, okay.
For example.
Okay, this one, let's say.
Point. At the top.
This one. This is alpha, this is alpha. So this is equal both ways. Equal, because the gravity is going to push this way and that way symmetrically. So it's alpha. Okay. Yeah, you can make it because what we wanted is we wanted the gravity to affect equally well both the branches. So if you tilt it, then of course there's going to be like two fields, so to say. I mean, the component of the field will have different values along the two branches. Yeah. Okay, maybe so that is so the kind of equation that is maybe
Standard one with some kind of
it's basically master equation. So it's basically master equation. So what you do is that okay, so you write down an equation for this guy. Let's say you define a quantity which is like this. Let me put it this way. Maybe I blocked this thing, no, or it just went away on its own, or?
No, we just.
Okay. You did the magic. No, it's okay. So, for example, if you can.
If you go some kind of normal topic description with some kind of transport.
No, so what we do, the way we do is that you write down the master equation for the propagator. What is the probability to be at this site at this time, given that I was here at an earlier instant? You write down the master equation. Okay, so that's not so difficult, but the question is to solve it. Okay, so what we do is that we go to the Laplace space, and in the Laplace space you can solve it exactly, simply because what happens is that you see you have this guy. Okay, now these are reflecting boundaries. Okay, because they have to come back. I have to make them reflecting. So what happens is that when I take the Laplace transform of the master equation, then since this is a reflecting, so what I can do is that I can relate the probability at these 2 points. Okay, and then I can go sequentially one by one and relate all the side probabilities on this branch to the corresponding backbone probability. But the problem that happens is that you end up with a continued fraction. I mean, you will have, you keep accumulating these numbers. So therefore, you will have a fraction, a continued fraction, and that is going to depend on the branch length. Okay? The thing is, I mean, the remarkable thing that we could do is to solve for that, have a closed form expression for that continued fraction. So eventually, in the Laplace space, what you can do is that you can reduce this problem to an effective problem of particles which are and like another thing I did not mention, that these are reflecting boundaries, but these is periodic. Okay, so effectively in the Laplace space you can reduce this problem to a problem of particle which is moving on a ring. Sorry. Yes, exactly. Yeah, so these information gets coded here in the probability here and so it effectively brings down boils down to a problem of a particle which is moving on a lattice. But of course these informations are not lost, they are there, and the thing is that you can solve this problem exactly. So the trick is to go to the Laplace space. That's one, that's maybe not so much a big deal. But the most important thing is you end up with, maybe I can tell you, so there is a continued fraction that comes about, and which we had a struggle to find an exact closed form expression for, which is, let me just see this one. Yeah, for example, let's say my structure is, let's say I want to know the probability here. Let me call this one, this is in the Laplace space. And since Luca is here, I should not use S for Laplace transform, so epsilon. Okay. And let's say this guy, this N is the backbone side, let's say, and this is. Okay. So this is the side probability on this branch side, and this is the side probability on this backbone side. And they are, they are related in the following manner. So there is this guy. So let's say this branch has, let's say, some ln number of sites. Okay. So this is gamma ln of epsilon of p tilde of n0 epsilon. But then this gamma ln epsilon is this, it has this kind of structure. So I write it down because then you will see that why it is difficult to explain. Oh, sorry. Okay. Minus by alpha of 1 divided by the structure repeats this epsilon plus alpha plus beta by alpha minus beta by alpha of, this guy repeats, but accepting that, this is of a finite length. I mean, it's not really an infinite continued fraction, simply because there are ln sites. So therefore, this will, in the denominator, you will have only ln number of terms. Okay. But the question is, how do I solve it? How do I get a closed form expression for this guy? And that can be done through a strange transformation that my student thought about, which is this: you define a new variable theta, which is square root of alpha by beta times s plus alpha plus beta divided by 2 alpha. I have no idea how did he come out with such a thing. And then this gamma ln, this you can solve it exactly. This comes out to be square root of, I mean, I want to write it down just to show how non-trivial it is. Let me define a quantity f, which is the ratio of the two operates. So it is sine hyperbolic of ln theta minus square root of f sine hyperbolic of ln minus 1 theta.
The exact value of the continuous fraction.
Yes, indeed. Minus square root of f sine hyperbolic of ln theta. So the real trick was to come up with the right transformation, because this way it cannot be just evaluated. Like, had this been an infinite one, then it would have been easy. But this has a finite number of terms. So how to compute it? So the way, how to make it simpler. So the way is to define this strange transformation cos hyperbolic theta, and then you have to really do a 3-4 page long calculation to show that this is the thing. And once this is known, then the rest of it is kind of not so difficult, because what this one allows is to express each of the branch side probabilities in terms of the corresponding backbone probability. So then you can, in the Laplace space, not really, in the Laplace space, you can reduce this problem to a problem of this. Okay? And then, well, if you are interested in the steady state properties, you don't really need the time dependent. You can use the final value theorem, multiply by epsilon, take the limit epsilon going to 0, and then the steady state distribution, probability distribution. In the steady state, what is the probability for the particle to be here or here or here or here? And once you know this, then of course the velocity is. And just one point that, in deriving this, I'm not using any self-averaging, nothing, for a given realization. So there's this factor gamma n, which is different for this guy, this guy, this guy, this guy, this guy, etc. And these numbers are given to me. These ln numbers, these are given to me. Yeah.
I would think this problem, because it seems to be independent, M and N. I would look at the product for the probability distribution as a product, some Qn times Rm, something, because
why they are independent? Because
N only depends on the length of N. It doesn't depend any way in any other way on N, right?
Yeah, if you are on this one, then you are saying that, okay, it doesn't depend on.
The length,
Mhm.
you don't need anything else. So
I
think you
don't-
can do some sort of,
Mean field
no,
approximation.
not mean field, it's look like separation of variables. Look for the solution
Uh-huh.
using separation of variables. Maybe it will simplify.
I think we did try this separation of variable. I got your point. This looking at this, and what I remember is that it didn't quite work out. We did look at it because we were thinking that, look, in fact, why we did it is because I did not mention this problem here, that the next thing that one would like to do is to have particles which have hardcore exclusion. Okay, because then what will happen is that, suppose a particle is here, it tries to go back, but this site is already occupied. So in that case, surely mean field approximation, I mean, these things get correlated. So in that context, we did look at it. And of course, that problem we could not solve it, because that makes it very complicated, simply because now you have to have information about, this site before you make a move.
Then that filling up the branches, you will have a transition.
Well, what happens is that if you, yes, what you have is that if you have interacting particles, hardcore exclusion, then you don't have this effect. I mean, the velocity is always non-zero. Doesn't matter what the bias is. I mean, it's all because of this thing that, there are these guys which are trapped here that take a very long time to come to the backbone, and that makes it. But, when you have hardcore exclusion, then this velocity is always non-zero, at least for the exponential case that I. We also looked at it with the stochastic resetting meaning that, you may ask, I mean, in this setting of probably Martin talked about, no, maybe not in this program, in the other program. So maybe stochastic resetting, did anyone talk about it?
Well,
Yes.
Yeah, but, oh, you're right. So the sun,
3 weeks
yeah,
ago.
the sun is.
Okay, I see.
No, but it was the convex hull.
He mentioned.
Oh, okay.
Mentioned the research.
So I'll mention something about this convex hull also. I mean, okay. So we also looked at it, let's say, non-interacting case. What happens? Can you avoid frapping by introducing stochastic resetting? And you do. For example, suppose you let these guys which are trapped here to make a jump here. Then of course, you come out. But that's kind of obvious that that's not so much of a. It doesn't matter. It doesn't matter. Okay, if you hop with a rate, I mean with a constant rate, that is, if your time intervals between two stochastic resettings are exponentially distributed. If you have a power law distribution, then what happens is that depending on the exponent of the power law, it may so happen that you may have to wait for a very long time for the resetting to kick in, and then you may remain trapped, etc. But for exponential, it just, and this calculation also goes. After this convex hull thing, so this I don't know. So this I was discussing with Debraj, and he said that maybe there's some relation with convex interface thing. That can you please bring that up? That this one. Maybe I try to. Achha. Yeah, this one. So it seems like, okay, so for example, given these points, so you can let's say you can draw a convex hull that that finds the outer whatever the that finds the outer boundary of these points. And the thing is that when you pull this, when this interface is going to move in this direction, it cannot cross that convex hull. And similarly in the backward direction also. So it seems like this motion is kind of bounded between two convex hulls. It's not really a closed convex hull, an open one, because if the way Satya describes that you have an elastic band and you just let it go, then what will happen is that that elastic band that I let go from the top is going to be pinned to these sides, this, etc. It won't reach out to this point. Okay. And so when you are pulling this interface, it's like the interface is going to grow in time, accepting that at every instant it remains bounded between the convex hulls of the, the configuration of closest points that it encounters in the forward and in the backward direction. I don't know since it is supposed to be an open discussion, so I don't know. So, but we have some, ways probably with your method this can be done. I mean that your walkers going this direction, etc., etc.
It was to work on in a more physical sense. So
Huh.
you are talking about columns, application for the media. There are equations for the equation, that's etc. What is the connection of your modeling with this type of distribution?
Actually, in Darcy's law, what they do is that they look at the output as a function of, so something is going to make its way through this porous media, and it looks at the output as a function of how much you push it from top. Okay. Well, one thing is that here I'm looking at a very microscopic way of doing things. I mean, those are like, I would say that, this feature is not so much tied to the particular model that you look at. The fact that you have a trapping beyond a certain critical bias, excepting for specifics, this is a very general scenario that if you have, trajectories that don't lead you from top to bottom and you try to push it from above, then, this kind of thing is going to happen generically. But specifics will of course depend on the particular model, the parameters of the model that you invoke to study the problem.
So what I'm confused about is you have to do sample averaging or you don't do sample?
I don't do sample averaging.
What usually if you do sample averaging, a lot of the results change, right?
Yeah.
But what is the correct thing to do? So is there can I ask this question?
Well, it depends on the correct thing to do, meaning that when the system is self-averaging and when it is not.
Exactly.
Okay. So the question is, it depends on the amount, the disordered distribution. That if the disordered distribution doesn't have a fat tail, okay, so then it is okay to do, an averaging, or, you will, a typical realization is same as, the average behavior. The typical behavior and the average behavior are going to coincide if your disordered distribution doesn't have fat tails. That is, you don't have rare realizations. Okay, exponential is one example. But if you have a power law distribution where, if the power is very small, let's say 1 by something k to the power 1 plus alpha, where alpha is smaller than 1, or let's say between 1 and 2, let's say where the variance is infinite, then typical behavior is very different from average behavior because the variance is infinite. And then it is dangerous to do an averaging because the averaging is not going to reflect the typical behavior. You may very well have realizations which behave very differently from the average behavior. This is the general paradigm of doing self-averaging vis-a-vis not doing self-averaging. Yeah.
If I do this plot,
Huh.
if I do average,
Hmm.
then it plots whatever if I do averaging.
Well,
Then there won't be any critical G or something.
I would think that if you do averaging, since we did it for an exponential distribution where typical behavior and average behavior are the same, then I would think that this behavior will remain.
No, I mean averaging of the structure itself.
Yes. It would remain the same.
Yeah, because
the lengths are always more or less the
the
same.
typical realizations are the same as the average realization. While if you do it for an exponential, then you may get a realization where there is no trapping. Yeah. While there may be realizations there where there are trapping. Yes, power law, yes. Power law, I mean, that's the bad thing about power. If the power is small enough, I mean, if it is like 1 by k to the power 5,000, then of course it doesn't matter. Variance and I mean, not 5,000, greater than whatever, 2 or 3. I mean, when the mean and the variance are finite, yeah.
Any other question? Okay, let's
Okay, thanks.